In the agenda for today, we're going to talk about modern technologies such as serverless computing, microservices, and containers, and where we expect them to be used, and the implications for using these sorts of technologies, particularly around vulnerability management programs, which most organizations adopt today. And we'll determine the likelihood of traditional pen testing methodologies working against these types of technologies. We'll also talk about the key security features which should be adopted for containerized deployments, and then also how to integrate them into your ongoing CI/CD deployment pipelines. We'll wrap up at the end with a couple of lessons learned and some key steps that people should be able to take on board going forward in the next few weeks to the next few months, both from the perspective of the buyer of security services, and also for those who have joined today and are deliverers of security services, such as penetration testers or people who perform security assessments or audits. There'll be some elements there to give you some pointers in where we expect that security assessments should be focusing. So one of the big questions today is, are containers as good as it gets? Now, in order to answer that question, I think we've got to peel back a few layers and look at the fundamentals of what actually a container is and where the security controls actually operate with it. The key thing to recognize with containers is that they're designed to virtualize a single application. Now, I've taken a definition from a common website, Search Cloud Security at TechTarget, and I've modified the definition with a couple of asterisks, which I'll show you in the next couple of slides, because what the intention of containers to deploy by design is not necessarily the way that it actually works out in practice. So, for example, if you've got an application such as a MySQL running in a container, the intention is for it only to deliver that particular application, in this case, MySQL, and it's intended to provide a virtual instance of that particular application. Now, the container should, with asterisks, create an isolation boundary at the application level rather than the server level. And that's because the container is an abstraction at the application layer. Now, the isolation should mean that if anything goes wrong in that particular container, it'll only affect that individual container and not the entire virtual machine or server for which all the containers are running on. So ideally, containers naturally and natively should provide a good level of isolation. However, it's not necessarily the way that it works out in practice. If you look at, and the reason being is that containers are actually very technically challenging areas to secure. If you look at Docker's own website, they provide 4 areas where security should be focused on. In particular, the intrinsic security of the kernel, the attack surface of the daemon itself, and they've got to look at the configuration profile of that particular technology, and also the way that the container and the operating system that delivers it have been hardened. Now, this isn't a presentation particularly about Docker technology, so let's look at things in a more technology neutral perspective. If we look at the intrinsic security of the kernel, we should be able to address that through supply chain risk management and vulnerability management practices. If you're using container as a service, using the platform as a service model from modern public cloud, then the intrinsic security of the kernel is no longer in your control. You're relying exclusively on the capability of the service provider to deliver you a secure container kernel. Reducing the attack surface can be managed through hardening, configuration, and vulnerability management. The container configuration itself is managed through configuration management, and hardening of the kernel and how it interacts with containers is delivered through hardening. Again, if you're using container as a service, you have no capability to manipulate the kernel itself. You've got to rely on the capability of the service provider who's delivering that platform to you. So as you can see, there are quite a few areas over here where organizations have to develop capability and expertise. Supply chain management, risk management, vulnerability management, hardening, configuration management, penetration testing, etc. Now let's explore a little bit where we expect to see containers operating in our modern environments. Historically, many organizations developed applications through a monolithic architecture. If you look on the left-hand side in this diagram, you can see that this is a very vertical or north-south view of the technology stack. In this case, you've got an interface, which for example would be a website. Behind it is sitting some business logic and access management layers, and behind that is the database where the data is actually stored. So in order to push data into the database or pull it out, the request has to traverse the entire stack in a north-south manner. That is called the traditional monolithic architecture. If we now consider today's modern microservices architecture, we will see that the architecture has changed. It is both north-south and east-west. That means that each particular component in the application is delivered by a discrete microservice, and each microservice might go and talk to a discrete function in the database or to another microservice within the application stack. In your modern microservices application, they may also broker their connection to the back-end application through an API gateway. In this case, you can see over here that your clients, which could be a web client, for example, a browser, a mobile device, or an IoT device, all make connections to the back-end application brokered through an API gateway. And if we look at these things side by side, on the left-hand side, we will see that the key difference between the monolithic application and the microservices application is that the monolithic application has code that runs in the same process, whereas in the API, within the API-centric microservices, each particular function is delivered through a discrete process, and those are shown in the yellow boxes where the services are running as containerized applications or containerized services. Now, a common representation of this is, for example, shown through the Microsoft eShop reference architecture. On the right-hand side over here, you can see that any client that is accessing the Microsoft eShop will be served content through discrete containers for identity management, catalog management, ordering, and even the shopping basket. And that's why we've circled each particular component as a container. That's because each function is discrete, and each discrete function can be delivered through a container or a number of containers if you've got a very large deployment. Now, to understand this, where the security is actually applied in a container and how an attacker might attempt to bypass that security, we've got to understand a little bit about the theory and the technical implementation of container technology today. Containerization is a form of virtualization and abstraction. The key difference between traditional virtual machines and modern containers is the point at which the abstraction occurs. If we look at the left-hand side, we can see that the hypervisor is the point at which the abstraction occurs in your traditional bare metal or type 2 virtualization system. That means that each individual virtual machine is actually delivered a slice or a component of the physical hardware. That means that the abstraction is occurring at the hardware layer and is delivered through the hypervisor. Whereas in the right-hand side, the abstraction is occurring at the operating system layer. That means that each container is delivered a slice or a component of an operating system. So containerization abstraction occurs at the operating system layer, whereas virtual machines, the abstraction occurs at the hardware layer delivered by a hypervisor. Now, the reason why this is important is because if we look at the following graph, we can see that as you move towards the bottom of the stack, you have an increasing order of complexity. Whereas if you move to the top of the stack, you've got an increasing order of abstraction. Now, there is obviously a point at which hardware and software intersect. If we look at our little rainbow graph over here, and we reveal it as we move up the stack, we'll see where the application sits. So first, at the bottom of the stack, you'll have some physical form of connection. Ultimately, even in cloud computing, you've got a server plugged into a switch through a piece of cable. You've also got technologies such as devices and transistors, which are sitting on your motherboards, gates and registers, a microarchitecture, and ultimately an instruction set, which then integrates with an operating system. On the operating system is running some machine code, and then as you get more progressive abstracted languages, assembly language, programming languages, algorithms, and ultimately the application sitting at the top of the stack. So today's modern web developer is trying to get a high degree of abstraction. As we can see in this diagram, modern web application development is akin almost to some sort of drag and drop function. That means that the web application development language is very much abstracted from the machine code that ultimately delivers the application running on the operating system. That means that developers today are at a race towards the top of the technology stack where there is a huge amount of abstraction, whereas the attacker, on the other hand, is in a race to the bottom of the stack. And the reason for that is that we've got the old saying, hooking lowest wins. That means that if you can get closer to the kernel of the operating system that you're trying to attack, you're more likely to get a stronger purchase on the operating system, and that means you'll be able to maintain persistence in the environment. So application developers are working towards the top of the stack, whereas a good hacker is trying to work towards the bottom of the stack. And this makes it quite a competing challenge between the two. Let's look at how this plays out in your modern microservices architecture with containers. In this diagram over here, we can see that it's a combination of both north-south vectors and east-west vectors. Now, the reason why this becomes important is because if you look at how a break-in might occur into your organization, it normally occurs through what we call a pinhole entry. In this case, the image is showing a bank vault with a small hole drilled into the side of the bank vault where the thief is trying to enter the bank vault to steal the money. This is akin to an application vulnerability on your public-facing application, probably a web application on a website. Once in the environment, the attacker then actually has to take the loot and leave the environment. Now, in this case, the attacker has got all the money, but they can't exit through the pinhole entry point that they came in at because the pinhole entry point is very small, whereas now they've got a lot of loot. So the attacker in this case has to leave basically through the vault door, which is locked. So if a container is doing its job and it should be containing the application, then ideally the vulnerability or the compromise of that vulnerability will be contained to a single container. However, a more sophisticated attacker will have the skills possibly to break out of the container that is designed to obviously contain the attack. And once you've got the ability to break out the container, you can then do what we call lateral movement, either going west or going east. So in order to move from out of the container in an east-west manner, the attacker has to do one of two things. Either they have to find a container vulnerability and exploit it, or they're going to have to find another mechanism. Let's describe first a little bit about the container vulnerabilities and exploits that are native to the operating system. Now, unfortunately, or fortunately, these don't occur very often. In fact, they're very infrequent. However, just a couple of months ago, there was quite a substantial container vulnerability that affected almost every container globally. And this was known as the run-C vulnerability. If you do a search on this particular CVE 20195736, you will see a lot of papers written up about this particular issue. And that's because this vulnerability, as we see over here, allowed a malicious container to overwrite the host run C binary and gain access to root level code execution on the host. In fact, there are a lot of interesting descriptions about this. I thought this one was quite interesting. They described it as a very, very, very bad privilege escalation to the host root. Now, it's not really a joke because it is a particularly significant vulnerability, and that means that if this particular issue was exploited, basically the attacker would have the crown jewels in your environment. And the kernel is not the only place where a vulnerability might occur. There are severe privilege escalation issues also in complementary technologies such as the orchestrating tools, for example, in this case, Kubernetes. Now, Kubernetes is just one of many orchestration platforms, and all of them have had vulnerabilities identified over a period of time. The alternative to breaking out of a container through a known vulnerability which is exploited is using a technique that we call living off the land. Now, if there is no vulnerability to exploit, then the attacker has to rely on misconfiguration of the container or an inflated container footprint to be able to use the tools within that container to be able to bypass the controls or the boundary conditions and move out of the container. This is what we call living off the land. Now, this takes a particular skill set within the attacker. So, for example, over here, we see some native bush people. Now, these are very resourceful people. They can find food in the desert and survive where most people might die of thirst or hunger within a couple of days. So they find little berries, fruits, and nuts, and everything to actually survive within a very hostile environment. The attacker in a containerized environment has to essentially do the same sort of thing. They've got to be able to find little components within the container to be able to exploit them and move outside of the container environment. Now, this takes a far more skillful attacker to be able to execute an attack in a containerized environment. There are other features of containers which make attacking them particularly difficult. We refer this to the low time to live function of a container. TTL is the acronym for time to live. Now, containers are what we call ephemeral. That means that they don't last very long in a modern computing environment. In fact, they might last only a few seconds to a few minutes, or maybe at most a few hours, which means that it's much harder for the attacker to maintain persistence in that environment. Unfortunately, it has also some other benefits. For example, if the containers move up and down very quickly, it does give you the opportunity to insert fresher images, and therefore vulnerability management could actually become easier because it becomes easier to actually deploy new and fixed systems at high frequency. On the other hand, there are some challenges that a low time to live gives you in your environment. For example, the fact that containers are ephemeral in nature means that forensics, log monitoring, information gathering becomes very difficult because the container might have disappeared before you had the time to actually collect the evidence or the logs off the machine. And also, in a constantly changing environment, it actually can be quite challenging from a vulnerability management perspective because you never know actually how many systems are active at any point in time. And for the same reason, configuration management can also be particularly challenging. So let's have a look at a little graphical representation of how time to live affects containers in the modern containerized deployment. I'll just run this simulation for the moment. You can see that on the right-hand side, application 4, the container changed state very quickly, whereas the container on application 2 remained active for the longest period of time. In this case, if the attacker wanted to have persistence, they would probably have a better chance of having persistence if they were attacking the application number 2 rather than app number 1. Let's run that simulation again and have a quick look at it. You'll see app number 4 is persistent for a period of time. App2 is persistent for the longest period of time, and the other ones are persistent for a much smaller period of time. Now, the attacker, of course, doesn't know which containers are going to have the longest time to live in the environment. So this makes the hacking attack all the more complicated. So now that you understand a little bit about the challenges of involved in performing penetration testing in the environment due to the ephemeral nature of containers, let's have a look at what you should be able to expect from a well-orchestrated penetration test. We'll also look at the implications to the supply chain risk and implications on container as a service offerings, and also how to integrate this into a DevSecOps end-to-end environment. On the left-hand side over here, we see Homer Simpson operating a rotary cannon. And on the right-hand side, we see the finesse of a surgeon with a scalpel. Now, ordinarily, one might think that Homer Simpson in this case is just basically shooting and praying, hoping that he might be able to attack an environment. It's not necessarily the case in this example. Homer Simpson is probably quite a well-qualified security consultant, probably on a six-figure salary, probably holding many certifications, and probably having operated in the industry for a number of years. But look a little bit closer, and you'll see that Homer Simpson in this example is actually operating with his eyes closed. That means that he actually doesn't understand the environment which he is trying to attack. He's performing this penetration test without any finesse at all. Now let's look at what the implication might be in a monolithic versus a microservices architecture. In a monolithic architecture, even operating with your eyes closed, you might be able to find a vulnerability that traverses the entire technology stack in a north to south manner and accesses the data in the database. An example over here could be a SQL injection attack. Whereas in the microservices architecture, you no longer have this north-south vertical movement. You actually have to be able to maneuver your way through the microservices ultimately to get to the database. So whereas in the monolithic architecture, a single vulnerability might have been able to get through all the way to the database, whereas in the microservices architecture, the attack is going to be deflected at many different levels before the attack ultimately gets to the database. In your modern application, the attack might be deflected at the perimeter through the next generation firewall or a web application firewall. It might be deflected at the container itself, and it also might be deflected between container instances. In this case, this image is showing the implementation of containerized firewalls between container clusters. So a particular attack is going to be reflected probably first at the perimeter, and secondly, as the attack attempts to maneuver horizontally through the environment, if you ever were able to extract yourself from the first container that you got into, then you have to maneuver your way through the maze of containers ultimately to get to the database where the data is. This means that to effect an attack and a penetration test in a containerized deployment with microservices is an intrinsically different undertaking to attacking a traditional monolithic application structure. And as you can see over here, that the attack in the microservices environment is going to be deflected at many different areas before the attacker is actually able to exploit the vulnerabilities. This means that the hacker actually has to transform themselves from the pinhole entry point, which is an application vulnerability, ultimately to an east-west attack, which is now essentially an infrastructure attack. This means that your attacker or your pen tester has to have the disciplines of both application pen testing capabilities as well as infrastructure pen testing vulnerabilities. And that means they have to understand also operating systems, applications, code, and how to live off the land with all those little components that might exist in container in order to effect the east-west attack. So obviously this becomes a lot more difficult, and we have to work all the way through from the top of the stack to the bottom of the stack to be an effective pen tester in this routine. So let's have a look at what the complexities are from the top to the bottom of the stack. At the top of the stack, you're ultimately going to have the user interface that people interact with. In this case, web applications, forms, logons, or APIs. Those things are ultimately delivered through frameworks, for example, struts or .NET. They're written in particular languages, Java, PHP, .NET, etc. And they are served by application servers, Microsoft IIS, Apache, Nginx, etc. And then there are going to be a series of containerized deployments which might deliver those. There are process containers at the presentation layer, process containers at the application layer, and at the backend layer. So a series of container deployments, as well as operating systems, and ultimately some clustering and orchestration technologies that actually manage the distribution of containers in the environment. Underneath those is your public cloud networking environment, the cloud platform itself, and ultimately the core infrastructure of your public cloud. For example, AWS, Google Cloud, or Microsoft Azure. Now, a vulnerability might exist in any one of those layers at any point in time. The job for the attacker is to be able to identify any one of those vulnerabilities from the top all the way to the bottom of the stack. Whereas from the defense perspective, you have to defend against all the layers in the technology stack. This means that performing an attack from the top layer of the technology stack all the way to the bottom layer of the technology stack requires a significant amount of knowledge, capability, and finesse. So if you are on the buying side of the procurement within your organization and you're actually procuring penetration tests, you've got to make discrete decisions about which supplier you're going to appoint to perform a penetration test. Clearly, as we've demonstrated here, performing a penetration test on a monolithic stack is a very different undertaking from performing a penetration test on your modern, highly distributed microservices technology stack. That's why we say there are pen tests and then there are pen tests. And you've got to really identify what sort of budget and capability you're seeking to engage in the marketplace. Your traditional approach is going to be lower cost, more predictable, won't really assess the threats, is only going to be capable in a north-south capability, not east-west, and is more for a checkbox audit, even though it might be delivered by a specialist firm delivering penetration tests. The more finesse that an organization has, their undertaking is going to be far more considered. It's going to require expert capability with a significant amount invested in research and development. The reason why this is because the attack actually has to basically enter through an application attack and exit through an infrastructure attack. And this requires a full understanding of the entire technology stack, including the platform in which it operates on, particularly if you're investing and implementing as a service technology. Also, this will require persistence in a very ephemeral setting because containers don't operate for a very long time in the market, in the environment. So obviously, this more considered finesse form of pen testing is going to cost more because it's going to take longer and require more skills. This will deliver appropriate assurance, validation, and ultimately determine if you're compliant with your own policies, procedures, and industry standards and obligations that you are required to address. So let's look at these things for the moment from the perspective of the blue team. The blue team is the defense team in your organization. They have to be able to manage the environment against the attackers who are attacking you on a day-to-day basis. Let's look first at end-to-end vulnerability management and then ultimately how you protect the container itself. Firstly, end-to-end vulnerability management. I'm sure by now, many of you have heard the terminology of shift left. Shift left means focus your attention closer to the source of the problem. If you can address the problem at the source, it's less likely to manifest itself in a production environment where the consequences of compromise are far more drastic. In this case, if you can address issues at the build stage for containerized deployments, the problems won't persist in the runtime environment. At the build phase, you've got to look at particular issues, for example, around third-party components. Where did you actually get the components that were built in, that were combined into your container? The registry itself can provide both public and private containers. Do you actually have confidence in the supply chain of the container that you're using? Do you understand the provenance of that particular container? Have you performed scanning of those containers to identify if there are any known vulnerabilities? On the host itself, there's obviously an operating system, and there are components within that particular container which might inflate the footprint of the container. So you might be running vulnerable components even if the intrinsic nature of your container itself is secure, but you might be running insecure daemons such as an insecure SSH daemon. And ultimately, when the container itself is running, there requires visibility at runtime, which means that you have to be able to perform audit logging and event logging on demand at runtime while the container actually doesn't operate for an extensive period of time. So your visibility in this case needs to incorporate everything from the build, registry, host, and the runtime. So let's look at where organizations need to focus their attention at this point. Firstly, they have to use trusted images. Endeavor to reduce the attack surface of the container, which is going to limit the possibility of live off the land attack, and ensure that they've got confidence in the third-party components that are incorporated into their containers. Supply chain risk in this place is a huge risk area. That means that organizations today, unfortunately, are not adequately identifying vulnerabilities that they're inadvertently incorporating into their containers simply because they just trust where the container and its components come from. In the implementation, organizations also obviously have to implement appropriate network segmentation. Orchestration tools such as Kubernetes today do actually help with network segmentation and a whole bunch of these other features, whereas managing the containers on their own don't provide that level of discrete capability. There are areas also across authentication in the containers. We've unfortunately today, many organizations still deploy SSH daemons in their containers, thinking that they need an SSH daemon to actually log into the container to manage it, whereas that's not really the case. You can manage containers today without having an SSH daemon to in order to log into it. So installing an SSH daemon just increases the footprint and increases the likelihood that there's another entry point into the application, and also one that might succumb to vulnerabilities over the course of time. And ultimately, once the environment is actually in production, you actually have to have ongoing security operations and advanced controls to make sure that in runtime, you've got the appropriate visibility actively. This is a screenshot of a commercial tool that is doing vulnerability scanning at the container level. In this case, it's identified that there is a high-risk vulnerability on that run C issue that I identified earlier in the presentation that was released back in February 2019. So technology such as this can be hooked into your SDLC and your DevOps pipeline to ensure that you've got visibility of the container and the applications running within the container environment. Ideally, organizations should not be running inflated container footprints either. You've got to endeavor to reduce the container attack surface, as we mentioned before. So for example, here around user access control, there is no requirement today to have SSH running in your modern container. Therefore, you can implement better user access control techniques rather than just inflating your footprint by running additional binaries that aren't necessary. And then, of course, you've got to harden the container to ensure that you've limited the potential for an attacker to deliver an east-west exploit. In this case, there are many tools that are available which can audit your container deployments against well-known standards such as the Center for Internet Security's benchmark and the NIST document, which I've referenced up here, 800-190. And of course, as we mentioned before, if you recall this image about the modern technology stack, you also have to ensure that you've got visibility at all layers within your cloud security stack. That means everything from the core infrastructure all the way up to the user interface, which ultimately delivers the application which you were intending to publish to the internet. So let's just do a quick recap of where we were and what we discussed today. We were talking about the overview of serverless technology, microservices, and containers in modern day technology. We compared microservices to the traditional monolithic technology stack and identified why containers have become so prevalent and prominent in today's modern cloud technology. We also looked and understood the nature of containers and where the abstraction occurs. In this case, container abstraction occurs at the operating system layer. We also understood why attackers tend to work towards the bottom of the technology stack, because if you hook lowest, you're going to get a persistent attack. Whereas on the other hand, developers are working to layers of higher degrees of abstraction at the top of the technology stack. Now, these things have got key implications for pen testing programs. The result is that you cannot rely on traditional pen testing techniques which would work in a monolithic attack structure, because a north-south attack is no longer going to be successful in a highly containerized or microservices deployment, because you might be able to find an entry point into the environment, but you won't necessarily be able to move out of the container that is delivering that particular application. We then described what are the key security features for container deployments, how to minimize the attack footprint, and how to harden your container deployments to ensure that you are not running inflated container images. We've then described how to integrate this into your CI/CD process to ensure that you've got end-to-end visibility on an ongoing basis, all of which can be automated without any human intervention. So let's see how we can apply what you've learned today in the next few weeks and few months. If you're in the executive or in the procurement function within your business, I recommend that you reset your review criteria for penetration testing. Explicitly incorporate the testing of cloud technologies into your vulnerability management program. If you are going out to market to look for pen testing capabilities, you should be able to review the supplier's capability in order to test the particular technologies that you are deploying. Remember that using traditional techniques such as that would work in a monolithic attack structure will not work in a highly containerized and microservices deployment. You should also be able to develop the blue team side of your operation. That means that you should be including technologies in your deployment which provide higher degrees of visibility in a shift left function in your end-to-end vulnerability management program. That means that you should be able to identify vulnerabilities closer to the source and prevent them ultimately from existing in your production environments. If you can do that, within 6 months, you should have been able to have performed an effective pen test of your cloud deployment, and also fine-tuned your blue team response to be able to identify the attacks in real time should they be occurring. If you're on the other side of the spectrum and you're actually a service provider in the space, but you aren't yet familiar with cloud technologies and containerized deployments, I recommend that you shortlist all the relevant cloud technologies that your clients use. You should be endeavoring to recalibrate your approach to pen testing containerized and microservices deployments. And this also becomes far more complicated when you're dealing with platform as a service, because there are many different types of service offerings depending on the particular cloud that your clients are deployed in. Within the first 3 months following this presentation, you should be able to have honed your skills and identified the capabilities to break out of containers, and also your ability to live off the land. That means that you should be able to look for functions within containers that aren't necessarily used, and be able to exploit those, the existence of them, to move in an east-west manner. Within 6 months, you should have been able to perfect a method to maintain persistence in a highly dynamic environment, and also work out how to work with your clients in a more collaborative approach, blending red team pen tests with blue team pen tests produces what we call the purple team assignment. This is quite an advanced technical undertaking where you're operating with your client both on the attacking and the defensive side to work out if they've actually got the techniques and capabilities to defend and attack real time. That brings this presentation to a close. We've got 15 minutes for questions, and I'm going to hand it over to Preetha and Priyanka at the moment to moderate the questions, and I'll be pleased to take them and provide any answers. Thank you.
Thank you, Murray. We have a few questions to start with. For the others, you can drop in your questions in the question panel or in the chat box, and we'll be taking it now for the next 15 minutes. Murray, the first question is regarding CISSP from M. Rao. I have sent it to you in the chat box. I could also read it out to you.
Okay, I'm just trying to access the chat box now.
Yep.
Okay, bear with me for a second.
Sure.
Okay, question 1. Which CISSP solutions can be used for ensuring container security? Well, personally, I'm not here to promote any particular technologies in the marketplace. Organizations have got different types of technologies that they might be using. Some organizations focus on commercial technologies, whereas others focus on using open source technologies. In the CISSP place, there has been a lot of consolidation in the marketplace, with a large number of the commercial players having invested in the CISSP space. You will have seen those make their announcement, and their portfolios are growing all the time. So in this case, I don't have any specific recommendations for commercial technologies, but I do recommend that you look at the major players in the space, because they are continually updating their portfolios to incorporate new technologies.
Great. Thank you, Murray. I'll just send you the next question. Some of you have a question whether we'll be sharing the recording. Yes, we'll be sharing the recording. I've sent you the second question, Murray.
Okay. This is a great presentation. Well, thank you very much. My question: what use cases should we keep an audit trail for containers and orchestration tools, so that our SIEM can detect and correlate the same? Okay, so what use cases should we keep an audit trail for? Well, let's look at the different technologies in your environment. There are operating system logs that you will need to be keeping log entries for. There is a runtime daemon that actually deploys the container itself. There's the application that runs within the container, Then you've got orchestration technology, which is used to ultimately manage the distribution of the containers in your environment. In addition to that, we also showed in some of the diagrams that you've got modern technologies, for example, container firewalls, which can manage pods and clusters of containers. You've also got the logs that actually are produced from the cloud platform itself. For example, your common public cloud, such as Microsoft Azure, AWS and Google Cloud, all produce logs at the platform layer. Each and every element of these logs across the technology stack have got varying degrees of information, all of which are useful, particularly in a forensics review, where if you have a problem in your environment, you need to ensure that you've got enough technical log information to be able to reproduce the attack to identify what had occurred. So ideally, all of these critical components should be producing logs at a level that gives you enough depth of view into what is actually occurring, where the entry point is into the system, where the system components that it touches, and where the data leaves your environment. If you can map all of those components together, you should be able to produce a good end-to-end visibility within your logging system.
Great. I've sent you another question.
Okay.
Question 3.
Are there any container native threat monitoring solutions that you could suggest? There are, and I recommend, for example, in Google has released a product called gVisor. gVisor is a product that ensures that only approved calls are made from the container through to the kernel. This is a great capability to identify inappropriate calls which are being made to the kernel, and Google provides that free of charge. Okay, I think we've got another one here. Thank you for the presentation. If a container is compromised through a runtime and a worm attempts lateral movement through the kernel, how is it detected in real time? And is there a recommended analytics engine for detecting the best target attributes or time to live for a container? Okay, that's an interesting question. Well, firstly, a worm might be able to exploit a known vulnerability, for example, the run-C vulnerability that was published in February. What you do have to have in place is the appropriate hook-ins to your platform, depending on the type of technology that you're using. You need to be able to get telemetry about all of the activity that is occurring at the runtime. This means that if you're using orchestration technology, you need to have monitoring at the orchestration level as well as at the per container level. All of these components together are going to give you a view which will enable you to identify things that are out of the ordinary. So first you have to have benchmark what you expect ordinary activity to be in your environment. You then need to have collected enough telemetry to understand what is out of the ordinary, and then drill down into those particular issues. Okay, question number 5. For performing container pen testing, what additional risks need to be considered in addition to the OWASP top 10 and SANS top 25? Okay, great question. Well, the OWASP top 10 is an web application specific program. That means that it's going to be looking to advise organizations, particularly around security of web applications. For example, input and output validation, session management, session handling, error logging, etc., etc. If you've got an infrastructure vulnerability in your environment that is independent of a web application, then OWASP has no relevance to the particular attack vector which might be used to circumvent.
Murray, I can't hear you. We lost you for around 10 seconds. I think, could you just reiterate the last question and answer?
Sure. The question number 5 is about performing container pen testing in relation to OWASP top 10 risks and SANS top 25. What I mentioned was that the OWASP is a very web application centric standard, and therefore if the attack vector is not attacking a web application, then the OWASP top 10 has no relevance to that particular attack. This is the reason why the attacker or the pen tester has to have skills both in web applications, because normally the container is delivering a web application at the presentation layer, but they need to have infrastructure capabilities outside of the web application. So once they exploit some form of web application, if that happens to be the entry point, then they have to be able to use infrastructure techniques to move east-west within the cloud platform. I trust that answers that question. Question 6. We have a microservice architecture and are planning to move to a containerized deployment on production from virtual machines. Yes. What are some of the top things we should keep in mind as we make the transition? Fantastic question. Well, let's go back to that shift left idea. The first thing that I would make sure that you do is that you focus on security at the source. You need to trust the container images that you're using. Are you building them yourself, or are you actually downloading them from some form of repository? If you're downloading them from a repository, you can't just trust them because they were published. You actually have to run scans against them to identify if there's any known vulnerabilities in them, including third-party component problems. In addition to that, I recommend that you start investigating security vulnerability management products that can scan the containers themselves and look at them during runtime. And also recommend that you consider container firewall technologies that can enable you to implement access controls between the containers within the pods and the clusters in which they operate. Okay. Well, thank you very much, everybody, for your attendance today. It was a great pleasure to deliver this webinar to you.